and they go to negative q qs minus q. So here qs is a certain line bundle on the next small on the conormal to the next smallest orbit, and I will say what it is. So so ys is this next smallest orbit. to u to the power of its length.
And second, for any element in the finite Hecke algebra, it commutes with this idempotent with this homomorphism, so this is the same as E times A, and this is equal to epsilon of A times E. So you see, it's not only almost idempotent, it's the basis element of a one-dimensional ideal. Okay? And finally, if we take the whole affine Hecke algebra and the corresponding left ideal, then this is a free module. Okay, with of rank 1. Okay, and the proof is evident for A, just from relations, right? Because we have relations that T S minus Q times Ts plus 1 is 0, and then you see that on the simple generators this works. There is such a homomorphism, and then from the other braid generators, it's well defined for any W. And now for B, let's. In fact, we've already made a similar argument a couple of times ago, but let's repeat it. So for a fixed simple generator, we have the splitting of the while group into two cosets with respect to this symmetric group on one generator. So here W prime are the log representatives. And the W double is the set of short representatives. Okay, and if we have an element in W prime, then W equals Sy for Y W double, and then we have TW is TS times TY, and hence TS times TW is TS squared TY, but for TS squared we have this equation, so it equals Q minus 1 times TW plus Q TY. And if W is in W second, then TS Y is just TSY. Okay. So now we can compute Ts times this idempotent. It is the sum over all W prime Ts T W plus the sum over Y W T S T Y. And so this is the sum over W prime Q minus 1 T W plus Q T something double prime W double like this plus the sum over W double T S Y, and then this is just the sum over W prime Q T W plus the sum over W double Q T Y, and so this is equal just Q E, and that's what we wanted to prove. Okay, so it remains to prove the last part. And for this, we know that the products like theta lambda T W for basis, the affine Hecke algebra, and the products like theta lambda E form a basis, or at least are linearly independent polynomials, but from B it follows that those products generate this ideal over polynomials, and there we are. Okay. So from this immediately it follows that this left ideal is an induced representation from the finite Hecke algebra to the affine Hecke algebra of this one-dimensional character. Okay, and this is our module M. The polynomial representation. Okay, and now geometrically we have the equivariant K group of the flag variety. It is isomorphic to the same thing. And we identified with our induced representation by the exponent of lambda goes to theta minus lambda times e. Okay, in the very beginning, in the definition of psi, that there was this negative sign. Okay, so now we'll formulate three propositions that will imply everything we need, but then we'll try to prove them. So the first proposition says that the polynomial representation is effective. That is the equivariant K-theory of Steinberg embeds into, so let's call it rho Z, into endomorphisms over representation ring of our group over this module. Okay, now the second proposition says that the diagram commutes the following one. So we have our generators, theta lambda and t w for finite Hecke algebra, and this set of generators certainly embeds into the affine Hecke algebra, and then there is a homomorphism to the endomorphisms again of this polynomial representation, and also there is this map psi that we just defined into the equivariant K-theory over Steinberg that goes to the endomorphisms of the same thing. So those two, well, it doesn't matter, in fact, endomorphisms over what, say over the base ring, but they're actually over this representation ring, but that's good as well. So these two are identified endomorphisms. And this diagram commutes. Okay. And now maybe let's immediately formulate a corollary. So this will prove today and next time, but corollary says that there is, so one may add the dotted line, dotted arrow, like this. No, not very much dot. Sorry. Like this. And this will be an isomorphism. So let's prove the parallel, though it's essentially evident. So we take the free associative algebra P, with generators W, and then there is a homomorphism tau to the Hecke algebra that sends generators to generators, and we have to check that well, there's also a homomorphism psi from this algebra, to the invariant K theory. So we have to check that if psi on the kernel of tau is 0. So we take an element in the kernel tau, and then maybe let's denote this like phi homomorphism. So then we know that the composition of phi and rho h and tau is 0, but on the other hand, it means that the composition of rho z with sigma of a is 0, but rho z is injective, so sigma of a is 0 because rho z was injective. That's how we use the first proposition. Okay. So now the last proposition is that this dotted arrow is an isomorphic. So let's start with the proof of the third proposition, and then move to the others. And it will be this follow the same route as for SL2. So we'll consider a filtration both on the Hecke algebra and on the equivariant K theory, and this dotted arrow will be compatible with this filtration, but on the associated graded quotients it will be an isomorphism. So let's extend the Brouwer order on the Weil group to a total order with the same notation, and set z less than or equal to W is the disjoint union of conormal bundles to the orbits smaller than W. Oh, sorry. Okay, and this is closed. Say that the smallest one is the conormal bundle to the diagonal orbit. And it is closed in the Steinberg variety. Okay, and again, last time we mentioned the cellular vibration lemma. About some short exact sequences, but at least it implies that the K theory of this embeds into the K theory of Z. Okay. And the images of these embeddings define infiltration in this covariant K theory of Steinberg with associated graded quotients. Just the equivariant K groups of conormal bundles to single orbits.
Здравствуйте, извините, вам немножко минут.
Здравствуйте. Okay. And now this orbit itself, well, this conormal bundle is a vector bundle. So this K theory is isomorphic to the K theory of this orbit itself. Okay, and this orbit itself is just an orbit with the stabilizer, the Borel subgroup, homotopically a torus. So it will be this equivariant K theory will be isomorphic to the K theory of torus. I mean, equivariant K theory of a point with respect to torus. So in other words, this will be a free module with a generator the class of the structure sheaf of this normal bundle. Okay, so this associated graded we understand pretty well, and the similar thing happens for the Hecke algebra because we know this Bernstein presentation. There is filtration like this. So it is spanned by the product theta lambda times TW, where, TY, where Y is smaller than W, and hence the associated graded is again a free R2 times star module would generate TW. Okay? And now we have to prove that under our map, this dotted map, TW goes to, I mean, in the associated graded, the class of TW goes to this class, or maybe twisted by some line bundle that is invertible. Okay. So, well, we have to check that the associated graded of psi isomorphism, and to this end we prove following lemma that first it makes sense so that the psi preserves these filtrations. Okay, and second, that on the associated graded, it is an isomorphism, so psi, the graded psi applied to TW is some scalar, invertible scalar times the class of this. Okay, so it's invertible element, so it's essentially just a character. Okay, in other words, the image of this TW will be not necessarily the structure sheaf, but class of some line bundle, equivariant line bundle. And then it doesn't matter because it is also a generator. Fine. So to prove this, we will need the de Mazur resolution. Say, Vanya, do you know de Mazur resolution by any chance? And Igor? So let me recall that de Mazur resolution. Well, the point is that Ys, as we know, Ys bar is smooth. So it's a P1 vibration over like variety. But if we take y w bar for arbitrary w or bigger length, then it's in general it's not smooth. I mean, if w is the longest element, then this closure will be the whole b squared and will be smooth again. But in general, it's never smooth. Well, So I wonder if I remember the simplest example when it's not smooth. Okay, so not smooth in general. So the simplest example maybe is for not complete flag variety, but parabolic flag variety. So it's Grassmannian 2, 4, but then certainly there's a projection from the flag variety of SL4, and if we produce a Schubert variety, say a singular Schubert variety here, its full preimage here will be also singular. So maybe now somebody knows this example of a singular Schubert variety in Grassmannian of SL4. In fact, just what are the Schubert varieties? In Grassmannian 2, 4, so we have two and there is a two-dimensional vector subspace in there. But we have to fix a flag. Like this. And the Schubert varieties are specified by the dimensions of intersections with this fixed flag. Okay? Or then if you so somehow we always switch between 2 points of view, and maybe later on today or next time we will do this somehow very in an industrial way. But so far, let me say that you can consider G orbits in the square of flag variety, or else you can consider B orbits in one copy of flag variety, and this is essentially the same problem, and the numeration will be the same, and the orbit closures will be equisingular, just say by intersection with one fiber here, or by inducing the other way around. So here I consider this more economical problem, where I have just one copy of Grassmannian, not two copies. But I consider so B orbits closures in one copy of this Grassmannian. And so I have to specify the relative position with respect to this flag. So that this Borel is the stabilizer of this particular flag. So there are the following possibilities. The smallest one is that V may just equal C2. There's just one point. Then there is a possibility that V is contained between C3 and C1. And this is just V1. Okay. Then there is a possibility that V is contained in C3, and this will be P2. There's a possibility that V contains C1, there's another P2, and there is one more possibility that neither of those happens, but still the dimension of intersection of V and C2 is at least 1. And this is, I don't know what. And finally, there's no condition whatsoever, and then we get the whole burst matrix. Okay, maybe let's call this Y. Maybe bar, Y bar. And this one will be singular. This orbit closure will be singular. And has two resolutions. So they're not quite de Mazur. I didn't define de Mazur yet. I will in 2 minutes. But they can be called de Mazur Zelivinsky. So it's some modification of de Mazur construction due to Zelivinsky. So what are these resolutions? Maybe somebody knows. So one of them, Y tilde 1, is the following moduli space of first lines that are contained in C2, but also they are contained in. Okay, so we know that this intersection has dimension at least 1. And we impose this by fixing this line. Now, if the dimension intersection is exactly 1, this is, in fact, the Borel orbit, the smooth part, then this line is necessarily just this intersection. So there is no choice. But if the intersection has dimension 2, then any line will do. And so we have that there is this projection. And the fiber, there is this singular point, but when V coincides with C2. Sort of, yes. So what is this point? Let's call it E. And the preimage is P1. Okay? And what is the second resolution? Any suggestions? Just Igor? Yes? Yeah, well, yes, it's dual. So V is contained in certain L, say, and this has dimension 3. So it's just literally dual. Okay, and again, for the same reason, the fiber over this singular point will be sort of dual P1. Okay, and as Ivan suggested, you can take the Cartesian product and this will be just the blow up at this point E of our singular Schubert variety, and in particular, well, if you use the Plücker embedding, you will see that this Y bar is a singular quadric, so when you blow it up, you glue in the projectivization of this singular quadric, which will be just two-dimensional projective quadric that is P1 times P1. The fiber over E is P1 times P1 dual is the projectivization of singular three-dimensional quadric. Okay. So this is an example of such a resolution. And in fact, Zlevinsky considered an arbitrary Schubert variety in arbitrary Grassmannian for SLN and constructed similar resolutions. You see, there is a variety of such approaches, but all the resolutions he constructed were very economical. You see, somehow this blow-up has two-dimensional fiber, but those guys have one-dimensional fibers, and they're called small because the fibers appear in codimension 3. This guy has dimension 3. And there is only a singular point in codimension 3, and the fibers in codimension 3 are only one-dimensional. It's called dimensionally small. So let me write down Zlevinsky. Constructed similar small resolutions for arbitrary Schubert varieties. In Grassmannian Kn. Okay. But unfortunately, or I don't know, maybe fortunately, for other groups, not SLN, and even for SLN, but other parabolic flag varieties, not Grassmannians, say complete flag varieties, it's impossible to construct smaller resolutions of singularities of Schubert varieties. So it's essentially the only generality when this works. But instead, there are non-economical de Mazur resolutions in the complete generality. So arbitrary Schubert variety in arbitrary flag variety or arbitrary group. So de Mazur resolutions. And we'll go back to complete flag varieties now, and to, in fact, the square of flag varieties. We'll have y w bar in the square of flag variety, and we'll take a reduced, we choose a reduced decomposition double equals S I1 S R so R is the length of W. And you see, here we also made some choices. There were two possibilities. And in general, there are much more possibilities. And then we define this resolution, y tilde, depending on this reduced decomposition. So this is just the Cartesian product, ys1 over the flag variety ys2 oh sorry, S I1, S I2, S IR. Okay, so you remember that for simple reflections, orbit closures were smooth. They were just P1 bundles over flag variety, both on the first projection and with respect to the second projection. So this is smooth, and so on. And you can take this Cartesian product, and it will be smooth, evidently. And also has an evident projection. Maybe P to this. Just I mean you forget everything inside. Only remember the first and last projection. And in fact, that is over the W. And say for SLN, it looks as follows. So you have again. Let me do it in this more economical version. So I will have just one copy of a flag, and the other one will be fixed. So I have C1 and C2, C. I don't know, I1 minus 1, C I1, C I1 plus 1, and Cn. And then I want a P1 bundle over this point to begin with, and this P1 bundle will be just moving this guy. So the next. So I will get a tower of P1 vibrations, right? So if we intersect with B one fiber, we fix somewhere else. We get a tower of P1 vibrations that projects onto YW, again intersected with B times 4L. Okay, so now I'm describing this tower of P1 vibrations, and this is the base, the first floor. I had the chaussee. So this will be this P1. I allow this to move between the fixed guys here. Okay, and let me call it V I1 maybe first, and the others are fixed. So it's V first I1 minus 1 is the same as here, and V first I1 plus 1 is the same as here, and V first 2 is the same as here, and so on. Okay, and now I'll continue like this. So at the last point, I will have V R minus 1 first, inside V R minus 1 second, and so on, and V R minus 1 I R minus 1, I r plus 1. Okay, and at the last step, I am allowed to move this guy while keeping all the others fixed. Okay, so this one is allowed to move. All the rest are the same. Okay, and then my projection to this economical Schubert variety closure will be just the last line. I forget all the intermediate steps. I only remember the last line. Okay, this is how it. So for example, say, well, let's take SL3, and let's take W naught equals S1, S2, S1, like this. Yeah, and then I start with the standard flag, 0 and C1, and C2 and C3. And then at the second step, I am allowed to move this one. Or maybe that one, sorry. V1, C2. And then in the second step, I'm allowed to move that one. So the same V1, maybe 1. But now it lies inside of V2, like this. And now at the last step, this one is still fixed. So maybe let's call it 3, 2. It is fixed, but I'm allowed to move this one. So altogether, I have a chain like this. So it's C1 containing V. It was C2 containing V11, and this is contained in V22, and this contains V31. Okay, and this will be my and this will be my resulting flag in the end. So I claim that any flag, any absolutely general flag in three-dimensional space can be obtained this way. I start with the fixed plane. I take some line in this plane. Then I take some plane containing this line. And finally, I take some line in this two plane. And these two form a most general flag. And moreover, if it's in general position with respect to this fixed one, then it can be done uniquely. All these intermediate steps are uniquely defined because of this. Okay, so we have this De Mazur solution. Yes. Pardon me?
There is the property of De Mazur resolution, but I'm not very sure of the memory. Is it true that the boundary of the De Mazur resolution is the normal crossing divisor?
Yes, it's the resolution in a very strong sense. Yeah, if there are some fans of algebraic geometry and resolutions of singularities, then what Roatao says is absolutely true, that that the preimage of the boundary the smaller Schubert varieties in this de Mazur solution is a normal crossing event. We will not need such subtleties. I mean, it is very important, and it is used throughout geometric representation theory, but in this particular case, we will not need it. Okay, so the support. So back to our business. We had this. We wanted to compute some associated gradient, yeah, and we're doing it now. So the support of convolution of sheaves on those conormal bundles to small orbit closures. Okay. Will lie in the intersection of the corresponding things in the conormal, in the cotangent bundle. So we'll take the conormal bundle of this as I1, and then well, let me use this notation. SIR. So I mean, you have to, just by definition of convolution, you have to lift something in the triple product, if you remember, and then you tensor in this triple product something. But certainly the supports they just intersect when you tensor, and I mean this circle means the intersection of things in the ambient variety, and this will be a closed subvariety of C, living over the corresponding thing in the base. Okay, and this thing will be exactly the closure of W of YW. So I mean, we just can ignore the conormal directions. It suffices only to keep track of the base in the flag variety. And then we will, again, we will use much more of this ideology. We will reduce the whole computation of relations to the computation, not in the cotangent bundle over flag variety, but in the flag variety itself. But here is very rough application, just for the supports. Okay, so hence this subvariety is of the form union of conormal bundles to y. Well, here for y less than or equal to w. Okay, because it lives in the closure of this Schubert variety. Okay. And in particular, it is the union of the desired part, the biggest cell conormal bundle to this, and something else which is closed in less than double. Okay, so the open part is just as we wanted, and there is some junk in the boundary that is in the smaller filtration piece, so we don't worry about this. Okay, and this implies that if we compute the convolution of our line bundles, QS1, SI1, and so on, QSIR. So these were some particular line bundles, yeah, the relative canonical class over those small orbits. We know that this has support in z less than or equal to w, and hence when we convolve their classes, we are in the desired convolution piece, and so we know that the convolution of theta of t s1, si1, psi of t sir also lies in the K group of z equal to w. Just because our generators went to the class of those line bundles plus some scalars, but scalars can only give smaller contributions in this filtration. So I already raised what we are proving, yeah. But the first part of this proposition 3 claimed that this conversion psi preserves filtrations, and that's what we proved. Okay, so we proved A. Okay, and now the more subtle point is B, when I have to compute the leading term of this convolution. So we know that psi of Ts restricted to the co-normal bundle to the open orbit. So I don't take the closure anymore. I take the open orbit. And then this is a line bundle Q. Yeah. So once again, this T goes to Q plus 1, but 1 is supported on the boundary here. So if we are only interested in the open part, then it's just the same line bundle Q, maybe multiplied by Q something. Okay, and then the point is that when we compute the composition in K theory, we must take tensor products and we lift those line bundles with supported on those conormals to say triple product or iterated product, and then take tensor product with something else. But the tensor product over these open parts will be somehow without any torus, because the intersections will be just transversal. And then you will acquire something supported on the iterated intersection, which will be just the usual product of line bundles. No higher torus, nothing else, because of this transversality property. So, I will define those supports in a moment. Let me just say first the intersection of the one is the R in the conormal bundle of B to the power plus 1 is transversal and equal to the conormal bundle to this open orbit under the projection number 1 R plus 1. So here those guys, the I is the projection to the I and I plus first entries, the preimage of this. Or maybe I shouldn't, sorry. Maybe I should. So I'm not sure this is the best way to write it, but maybe at least you understand what I mean. I'm sorry. I mean, I wrote SI something, and now okay, maybe let's this way. The L is 1, and here is SL. Okay, and now I think maybe SIL. Yeah. Now I think it is the same. So it's 1, 2, 3, 4, 5 hierarchy of subindexes. Okay. Okay. And this projection is L plus 1 is you understand what? Fine. And now let Q SIL will be the direct image of L under the embedding the L into this cotangent bundle. And then finally, the convolution of our generators restricted to this open part. Is just the product of those line bundles. One SIR. Okay, the product of line bundles. And hence it is a line bundle. And hence invertible. So the class of this is what we denoted CW, and proposition is proved. So once again, the idea is that we perform some complicated operations. So we have, let's say, when length is 2, what do? We have one copy of this, another copy of this, and a third copy of this. So we have to take something in here and pull it back along the third projection. Also take something in here and pull it back along the first projection, and then we have to tensor them inside, by the definition of convolution. So I claim that in the open part, away from the boundary, the supports of those pullbacks intersect transversally, and so the pullbacks just tensor in the most naive sense. There is no higher torus, nothing. So we tensor just line bundles, and fine. But then what we have to do? Then I have to project onto the first and third factors, right? We have to integrate over that. But fortunately, under this projection, it is just an isomorphism. That was the point of the de Maisel resolution. Okay, so again, nothing happens. There's just an isomorphism, and whatever line bundle we had on this intersection goes isomorphically to the same line bundle on the open Schubert cell. Okay, so there is hard part on the boundary. We know nothing about this, and this will be the subject of later research. But model of the boundary, this is all very straightforward. Okay. Okay. Now I have 5 minutes left, and yeah. Well, maybe let me start something. I will have to repeat it next time anyway, but at least. So we have canonical presentation of K-variant K-theory of the standard variety of triples, and namely, this will be the K equivalent with respect to Borel times C star of certain Borel version, and this will be the same as KT C star of the same Borel version. Now, Borel version Z B is just the union of conormal bundles again to Schubert cells BW in one copy of like variety. B orbits for the fixed Borel. Okay, and then I claim that we have the following for example, the following embedding. This goes into the partial cotangent bundle and just the second copy of B, but still there is an embedding, right? Because the variety of triples was one nilpotent and two Borels. Here you have one nilpotent and two Borels, and this projects onto B, and this guy Z B is the fiber of this composition over this particular point in the flag variety. Okay, so we have the following diagram. This embeds into this partial product. On the other hand, there is an embedding of zero section here and projection onto the flag variety. And here is an embedding of this economical version. Okay, and embedding I of the flag variety times this point, and again there is a projection onto this point, and there are embeddings like this. So here everything is fibered over B. For the flag variety. And here we just take fibers of the first line over a particular point. Okay. And then the claim is that whatever we could say about, well, this is the claim. And we can also define the convolution in terms of this. So this was more symmetrical version, right? Here we fixed some Borel, and it is not so symmetric, but it's more economical. The size of the variety of triples is smaller. Okay, so it will help us in some technical respects next time. But also, if you remember what I said last time about double affine чередник Hecke algebra, it is this Bernstein construction applied to the affine Hecke algebra in place of finite Hecke algebra. But again, it can be geometrically obtained in the similar vein, only you replace G by the affine group, yeah, the loop group. And then, for example, for the loop group, there is no such notion as a covariant K-theory. Nobody knows how to define a K-theory covariant with respect to the loop group. So for finalization, this thing does not exist. But here you have a Vahori, and this exists perfectly well. So in the affine case, this does make sense. This economical version works in the affine case, and you can construct geometrically double affine Hecke algebra this way and classify its representations following our scheme. But you cannot do it in this invariant symmetric form, only in the economical form. So it has some use in it, apart from the technical use we'll apply next time. Okay, thank you.